Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Throughout human history, we've gazed at the stars with wonder, constructing narratives about our place in the cosmos. But modern astrophysics reveals a universe that operates with magnificent indifference to our existence. What's truly unsettling isn't just our cosmic insignificance, but the realization that the universe could vanish without the slightest warning. The scientific community has identified several cosmic doomsday scenarios that might unfold instantaneously, offering no chance for preparation or farewell. These aren't drawn from science fiction, but emerge from the cutting edge of theoretical physics, where our understanding of quantum mechanics, cosmology, and fundamental forces converges. When we consider the end of everything, we often imagine gradual processes, the sun expanding to consume Earth in 5 billion years, or the slow heat death of the universe trillions of years hence. But what if the end came not with a whimper, but without even the chance for a bang? The first scenario involves vacuum decay, a phenomenon rooted in quantum field theory. To understand this concept, we must first acknowledge that what we perceive as empty space is actually a quantum vacuum, a seething cauldron of virtual particles popping in and out of existence, governed by fields that permeate all of space-time. Our universe exists in what physicists call a false vacuum state. Like water that remains liquid below freezing point under certain conditions, our vacuum may be metastable, temporarily stable, but not at its lowest possible energy state. If a small region of space were to tunnel to a lower energy state, the true vacuum, it would create a bubble of altered physics that would expand outward at the speed of light. Within this bubble, the fundamental forces, physical constants, and perhaps even the dimensions of space-time would be radically different, incompatible with the existence of atoms, let alone complex life. The boundary of this bubble would be a wall of absolute destruction, converting everything it touches into this new state of reality. The terrifying aspect of vacuum decay is that we would never see it coming. Since the boundary cannot move faster than light, no warning could outpace it. One moment we would exist and the next, without sensation, without realization, we would not. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Some theoretical physicists, including Nobel laureate Joseph Polchinski, have calculated that vacuum decay might be more likely than previously thought. The discovery of the Higgs boson in 2012, with a mass of approximately 125 giga-electron volts, places our universe tantalizingly close to the stability boundary. The difference between stability and metastability hinges on extraordinarily precise measurements of the top quark's mass. Uncertainty still exists, leaving open the possibility that we live in a universe that could collapse at any moment. What's more unsettling is that quantum fluctuations occur constantly throughout the universe. If just one of these fluctuations in any corner of the cosmos triggers the decay of the false vacuum, the resulting bubble would eventually reach us, rewriting the laws of physics in its wake. The universe as we know it would cease to exist, replaced by something wholly alien. Vacuum decay represents just one quantum catastrophe that could end our universe without warning. But it's not alone. The quantum realm, with its inherent uncertainties and probabilistic nature, harbors other potential doomsday scenarios that current physics cannot dismiss. Consider the bizarre phenomenon known as quantum tunneling on a cosmic scale. In quantum mechanics, particles can tunnel through energy barriers that would be insurmountable according to classical physics. This isn't theoretical. Tunneling happens constantly in nuclear fusion within stars and enables technologies like scanning tunneling microscopes. What's unsettling is that quantum mechanics applies to everything, not just subatomic particles. In principle, there's a non-zero probability that all the atoms in your body could simultaneously tunnel to another location, or that Earth could suddenly tunnel into the Sun. These probabilities are incomprehensibly small, effectively zero, in any practical sense, but they're not mathematically zero. Now scale this concept to the universe itself. Some theorists propose that our entire cosmos could quantum tunnel into a completely different configuration. The mathematics suggests this would happen instantaneously across the entire observable universe. Unlike vacuum decay, which propagates at light speed, this transformation wouldn't need to spread. It would simply happen everywhere at once. Another quantum consideration involves the Heisenberg uncertainty principle, which states that certain pairs of physical properties cannot be precisely measured simultaneously. This isn't a limitation of our measuring instruments, but a fundamental feature of quantum reality. One such pair is energy and time. The energy of a system can fluctuate wildly over extremely short timescales. These energy fluctuations typically average out over longer periods, but theoretically, the energy of the entire universe could spontaneously spike due to an extraordinarily unlikely quantum fluctuation. If the universe were to experience such a massive energy fluctuation, it could trigger a phase transition that would reconfigure the fundamental forces instantaneously. Quantum field theory suggests our universe consists of overlapping fields that interact constantly. The electromagnetic force, the strong and weak nuclear forces, and gravity are expressions of these fields. Normally, these interactions maintain the stability of our physical laws, but a sufficiently large quantum fluctuation could disrupt this harmony. The concept of quantum non-demolition measurements might offer a parallel. These are special observations that don't collapse quantum states in the usual way. Some physicists speculate that the universe itself could be subject to a form of cosmic observation that could precipitate an instant phase transition. What's particularly disturbing about these quantum catastrophes is their fundamental unpredictability. The same quantum uncertainty that prevents us from knowing both the position and momentum of a particle with perfect precision also prevents us from predicting when or if our universe might undergo a spontaneous quantum transformation. Recent work at the interface of quantum gravity and cosmology has begun exploring these questions more rigorously. Theoretical physicists like Hiranya Piris at University College London are developing methods to search for signatures of quantum transitions in the cosmic microwave background, the afterglow of the Big Bang. If our universe has undergone smaller quantum transitions in the past, evidence might be encoded in this ancient radiation. The standard model of particle physics, despite its remarkable success, doesn't fully account for dark matter, dark energy, or quantum gravity. These gaps in our understanding leave room for additional instabilities that could manifest without warning. The universe might be balanced, on a knife edge of stability, with quantum fluctuations constantly testing that balance. Moving beyond quantum catastrophes, we encounter another class of potential universal destroyers: topological defects in the fabric of spacetime. These exotic structures emerge naturally from our best theories about the early universe and could harbor apocalyptic potential that would manifest without warning. Cosmic strings represent one such defect: hypothetical one-dimensional lines of concentrated energy that may have formed during phase transitions in the universe's first moments. Unlike the familiar strings of string theory, cosmic strings are macroscopic objects that could span the entire observable universe. These strings would carry enormous energy, roughly 10 to the 22nd kilograms per meter, equivalent to the mass of a small planet compressed into a strand thinner than a proton. If cosmic strings exist, they could potentially intersect or form closed loops. When cosmic strings interact, they can generate gravitational waves of tremendous power. Calculations suggest that if two cosmic strings were to cross paths near our solar system, the resulting gravitational disturbance could tear apart our local space-time without any advance notice. Theoretical physicists like Alexander Vilenkin at Tufts University have shown that cosmic strings could move at nearly the speed of light. A cosmic string passing through our solar system would create a gravitational discontinuity that could instantaneously disrupt the orbits of planets, potentially ejecting Earth from the solar system or shredding it through tidal forces. Domain. Walls represent another class of topological defect: two-dimensional structures that could form boundaries between regions of space with different fundamental properties. These cosmic membranes would carry even more energy than cosmic strings and could exert repulsive gravitational effects on normal matter. If our universe contains domain walls, we might live in a cosmic bubble bounded by these structures. The collision of our bubble with another domain wall could instantly rewrite the laws of physics throughout our observable universe. Since domain walls could move at relativistic speeds, their approach would be undetectable until the moment of collision. Perhaps most exotic are magnetic monopoles, hypothetical particles carrying a single magnetic pole, either north or south, rather than the dipole structure found in ordinary magnets. Grand unified theories predict these particles should have formed during the extreme conditions of the early universe. Theoretical calculations suggest monopoles would be extraordinarily massive, roughly 10 to the 16th times heavier than a proton. If a magnetic monopole were to pass through a region containing normal matter, it would induce powerful electromagnetic disturbances. The magnetic field around a monopole is inverse square, meaning it doesn't diminish as rapidly with distance as a dipole field. A monopole passing near Earth could potentially disrupt our planet's magnetic field, exposing us to deadly cosmic radiation and solar wind. These topological defects share one disturbing commonality. They could travel at relativistic speeds, meaning we would receive no warning before their arrival. Our first indication of their existence would likely be our last moment of consciousness. Recent observations from cosmic microwave background experiments like Planck and Bicep Pot Keck have placed constraints on the abundance of cosmic strings and other topological defects, but they haven't ruled out their existence entirely. The hunt continues with gravitational wave detectors like LIGO, Virgo, and the future space-based LISA mission, which might detect the distinctive gravitational wave signatures of these cosmic anomalies. The most unsettling aspect of topological defects is their persistence. Unlike quantum fluctuations that might be vanishingly rare, cosmic strings and domain walls, if they exist, are guaranteed by our theories to be traversing the universe right now. Our continued existence may simply be a matter of cosmic coincidence that none have yet crossed our path. Beyond quantum effects and topological defects lies another category of cosmic threats: relativistic kill mechanisms and high-energy cosmic phenomena that could eradicate life instantaneously across vast distances. The universe harbors objects and events capable of projecting destructive energy across thousands or millions of light-years, often with little or no warning. Gamma-ray bursts, GRBs, represent the most powerful explosions known in the universe. These cataclysmic events release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. Astrophysicists classify them into two categories: long-duration bursts lasting more than 2 seconds, typically associated with the collapse of massive stars, and short-duration bursts lasting less than 2 seconds, often linked to the merger of compact objects like neutron stars. The energy from a GRB is highly collimated, forming jets that can travel billions of light-years through space. If Earth were caught in the path of such a jet originating from within our galaxy, the consequences would be apocalyptic. The burst would deposit enormous energy into our atmosphere, triggering a cascade of nitrogen oxides that would destroy the ozone layer and potentially initiate a global cooling event. What makes GRBs particularly insidious is their unpredictability. The beams travel at nearly the speed of light, which means we would receive the devastating radiation at essentially the same moment we optically detect the explosion. There would be no time for preparation or evacuation, not that either would help against such overwhelming energy. Magnetars present another relativistic threat. These exotic stellar remnants are neutron stars with magnetic fields 1 trillion times stronger than Earth's, powerful enough to distort atomic structures and fatal to living organisms from thousands of kilometers away. Occasionally, magnetars experience starquakes that release tremendous bursts of energy in the form of X-rays and gamma rays. In 2024, a magnetar designated SGR 180620 produced a flare so intense it ionized Earth's upper atmosphere from 25,000 light-years away. Had this event occurred within just a few light-years of our solar system, it could have triggered mass extinction. The disturbing aspect is that astronomers estimate our galaxy contains approximately 30,000 magnetars, most of which remain undetected due to their normally quiescent state. Equally concerning are relativistic jets from active galactic nuclei, AGNs. At the centers of many galaxies, including potentially our own Milky Way, lie supermassive black holes. When these black holes actively accrete matter, they can generate jets of particles accelerated to near light speed. These jets extend thousands of light years into intergalactic space and carry enormous energy. The galaxy Messier 87, imaged by the Event Horizon Telescope in 2019, displays a prominent relativistic jet extending more than 5,000 light-years from its central black hole. If our solar system were to pass through such a jet, which could happen if the Milky Way's central black hole suddenly became active, Earth would be subjected to a barrage of high-energy particles that would irradiate the planet's surface. Perhaps most concerning is our inability to predict when dormant black holes might become active. Historical records suggest the Milky Way's central black hole, Sagittarius A star, has experienced periods of activity in the past. A sudden awakening could direct a relativistic jet toward Earth with no astronomical precursors visible to us. Beforehand, false vacuum decay discussed earlier could also be triggered by high-energy cosmic phenomena. Theoretical models suggest that the concentrated energy in cosmic ray collisions or at the event horizons of black holes might be sufficient to nucleate a bubble of true vacuum. If correct, these astronomical events could serve as cosmic triggers for a more fundamental unraveling of reality. The most unsettling aspect of these relativistic kill mechanisms is their democratic nature. They would affect all life simultaneously, regardless of technological advancement or protective measures. Against such cosmic violence, our planetary defenses are non-existent. Moving beyond phenomena within our observable universe, theoretical physics suggests even more profound threats might originate from beyond the boundaries of our cosmic horizon or from higher dimensions. These scenarios emerge from string theory, M-theory, and various multiverse hypotheses, frameworks that remain theoretical but continue to gather supportive evidence. String theory postulates that our universe has additional spatial dimensions beyond the three we experience, compactified to submicroscopic scales. In some variants of string theory, particularly brane cosmology, our entire universe exists as a four-dimensional brane floating within a higher dimensional bulk space. Other brane worlds might coexist with ours in this higher dimensional realm. The ekpyrotic scenario, developed by physicists Paul Steinhardt and Neil Turok, proposes that the Big Bang resulted from a collision between our brane and another. Such collisions could occur cyclically, with each impact essentially resetting the universe. If this model is correct, another brane could be approaching ours right now through dimensions we cannot detect. When two branes collide, the tremendous energy released would instantaneously restructure space-time throughout our observable universe. The collision would propagate at the speed of light, but since it would emerge from every point in space simultaneously, there would be no warning, no astronomical precursors, no gradual changes in physical constants. One moment the universe would exist, and the next it would be fundamentally transformed. The many worlds interpretation of quantum mechanics offers another mind-bending possibility. This framework suggests that quantum events don't collapse into a single outcome, but instead cause reality to branch into multiple universes, each representing a different outcome. Theoretical physicist Max Tegmark has proposed that these parallel realities might not be entirely separate. Quantum decoherence normally keeps them distinct, but some mechanism might allow interaction between branches. If quantum barriers between parallel universes were to break down, the consequences could be instantaneous and universal. The mathematics suggests that such an event would manifest as a sudden phase transition affecting quantum probability throughout the entire cosmos. The mathematics of quantum mechanics would remain valid, but all probabilistic outcomes would change instantaneously, potentially rendering matter as we know it unstable. Another multiversal concern emerges from eternal inflation theory. This model suggests our universe is just one bubble within an eternally inflating superspace. Other bubble universes with potentially different physical laws might occasionally collide with ours. Theoretical physicist Anthony Aguirre has calculated that such collisions would produce detectable circular patterns in the cosmic microwave background. And intriguingly, some candidate patterns have been identified, though none definitively confirmed. Even more exotic is the holographic principle, which suggests our three-dimensional reality might be encoded on a two-dimensional boundary, similar to how a hologram projects three-dimensional information from a two-dimensional surface. If our universe is holographic, disturbances in the boundary encoding could propagate through the entire projected cosmos instantaneously. Recent theoretical work by Yoshifumi Hyakutake and colleagues has found mathematical evidence supporting the holographic principle, showing that quantum information theory in a lower dimensional space can reproduce gravitational physics in higher dimensions. If correct, this suggests our reality is more tenuous than we imagine, a projection that could be disrupted by events occurring in dimensions we cannot perceive. The challenges in detecting or predicting such multiversal catastrophes are fundamental, since these threats would originate outside our observable universe or in dimensions beyond our perception. No astronomical observations or physical experiments could provide warning. Our most sophisticated theories, including quantum gravity and string theory, remain incomplete, leaving open the possibility that reality harbors instabilities we haven't yet imagined. The study of these existential scenarios isn't just theoretical indulgence. It pushes the boundaries of fundamental physics and cosmology, potentially leading to breakthroughs in our understanding of reality. The search for a theory of everything continues, driven partly by the hope that a deeper understanding might reveal whether our universe truly is as precarious as current theories suggest. While quantum effects, topological defects, and multiversal collisions could destroy our universe through spatial mechanisms, time itself might harbor instabilities capable of unraveling reality without warning. The nature of time remains one of physics' great unsolved mysteries, and several theoretical frameworks suggest it might be vulnerable to catastrophic disruptions. Einstein's general relativity established that time is not absolute, but relative, woven into the fabric of spacetime, and affected by gravity. This revolutionary understanding opened the door to exotic phenomena like closed time-like curves, CTCs, theoretical paths through spacetime that return to their starting point in time, effectively creating time loops. Physicist Kip Thorne demonstrated that certain spacetime geometries, particularly those involving exotic matter with negative energy density, could support traversable wormholes and CTCs. While creating such structures might require technology beyond our current capabilities, they might occur naturally under extreme conditions near black holes or in the early universe. The troubling aspect of CTCs is their potential to introduce causal paradoxes, situations where cause and effect become circular or inconsistent. Theoretical physicist Igor Novikov proposed the consistency principle, suggesting that nature prohibits paradoxes, but this remains an unproven conjecture rather than a fundamental law. Some theoretical models suggest the universe might enforce temporal consistency through chronology protection, as hypothesized by Stephen Hawking. This protection mechanism would prevent paradoxes by destabilizing spacetime near potential CTCs, causing them to collapse before they can form. However, Hawking's chronology protection conjecture remains unproven within quantum gravity. If chronology protection fails, or if it operates through a catastrophic mechanism, the consequences could be instantaneous and universal. A causal paradox at any point in spacetime could trigger a cascading breakdown of causal order throughout the universe. The distinction between past, present, and future would dissolve, rendering conventional reality impossible. Time instabilities might also emerge from the thermodynamic arrow of time. The second law of thermodynamics, that entropy always increases in closed systems, gives time its apparent direction. Theoretical physicist Sean Carroll has proposed that our observable universe might be just one region within a vastly larger, Multiverse with different entropy gradients and consequently different arrows of time. In this framework, the boundaries between regions with opposing temporal arrows could be unstable. If our cosmic region were to collide with another region where time flows backward, from our perspective, the entropy gradient defining our arrow of time could dissipate. Without a consistent entropy gradient, time would lose its directionality, and causality would break down. Another possibility emerges from quantum gravity theories, particularly loop quantum cosmology. These frameworks suggest spacetime has a discrete, granular structure at the Planck scale, approximately 10 to the e-35 meters. This quantum foam of spacetime might undergo phase transitions similar to those in ordinary matter, potentially altering the mechanisms that maintain temporal continuity. Recent work at the interface of quantum information theory and cosmology suggests information might be fundamental to reality, with spacetime and physical laws emerging from quantum computational processes. If this perspective is correct, temporal stability might depend on the continuous processing of quantum information. A sufficiently large quantum fluctuation could disrupt this processing, causing a universal crash of reality, analogous to a catastrophic computer system failure. The Wheeler-DeWitt equation, a foundational formula in quantum gravity, notably lacks a time parameter entirely, suggesting that time might be emergent rather than fundamental. If time is indeed emergent, it might be vulnerable to discontinuities that our current physical theories cannot predict. These temporal instabilities share one disturbing characteristic: they could manifest without warning throughout the entire universe simultaneously. Unlike spatial threats that propagate at light speed, causal disruptions could affect all of spacetime instantaneously, as the very mechanism that enforces sequential causality would be compromised. The study of these temporal doomsday scenarios remains largely theoretical, but it drives research in quantum gravity, cosmology, and the foundations of physics. Each theoretical advance brings us closer to understanding whether time itself might harbor catastrophic instabilities that could end reality as we know it. Having explored various scenarios for how the universe might end without warning, from quantum fluctuations and vacuum decay to cosmic strings, relativistic kill mechanisms, multiversal collisions, and temporal instabilities, we're left with profound questions about how to contextualize our existence within this framework of cosmic uncertainty. The first sobering realization is that many of these doomsday scenarios are not merely hypothetical. They emerge naturally from our most successful physical theories: quantum mechanics, general relativity, and the Standard Model of particle physics. While uncertain in probability, they represent genuine possibilities within current scientific understanding. The vacuum state of our universe, for instance, appears to be metastable according to the best measurements of the Higgs boson and top quark masses, suggesting vacuum decay is physically possible. Yet paradoxically, the very imperceptibility of these apocalyptic scenarios offers a peculiar comfort. If the end could come without warning, instantly and painlessly, does foreknowledge serve any purpose? There would be no suffering, no gradual decline, just an instantaneous transition from existence to non-existence, or perhaps to some entirely new state of reality incomprehensible to our current physics. From an evolutionary perspective, our brains develop to assess immediate threats: predators, hostile tribes, environmental hazards, not esoteric quantum or relativistic catastrophes. Our intuitive risk assessment capabilities falter when confronted with threats that operate outside our perceptual framework. Perhaps this mismatch explains our collective difficulty in addressing long-term existential risks like climate change or nuclear proliferation. Threats we can understand, but struggle to respond to proportionately. The philosophical implications run deeper still. The potential for instantaneous universal destruction challenges our conceptions of cosmic justice, purpose, and meaning. It raises questions that verge on the theological. Is a universe that could vanish without warning fundamentally absurd? Or does the precariousness of existence make conscious experience all the more precious? Physicist Brian Greene suggests that our very impermanence, both individually and potentially cosmically, gives meaning to existence rather than negating it. The transience of conscious experience in an indifferent universe makes appreciation of that experience more profound. We value the rare and fleeting above the guaranteed and eternal. From a scientific perspective, these apocalyptic scenarios are valuable not primarily for their doomsday implications, but for the theoretical insights they generate. The study of vacuum decay advances our understanding of quantum field theory. Investigations of cosmic strings illuminate cosmological phase transitions. Analyses of causal paradoxes clarify the nature of time itself. Science progresses by exploring the boundaries of current understanding, even when those boundaries reveal existential vulnerability. Some theorists propose the anthropic principle as a response to cosmic uncertainty. Since we exist to contemplate these scenarios, we must live in a universe where they haven't yet occurred. This principle, while logically sound, offers little predictive power about future stability. It explains our existence up to the present moment, but says nothing about tomorrow. The concept of cosmic humility emerges from this analysis, the recognition that despite our scientific achievements, we remain fundamentally limited in our ability to predict or control ultimate cosmic events. This humility need not lead to nihilism or despair, but might instead inspire a deeper appreciation for the extraordinary conditions that allow conscious beings to exist at all. Indeed, the very fact that we can comprehend these abstract threats represents a profound achievement of the human mind. We are, as Carl Sagan noted, the universe's way of knowing itself. For a brief moment in cosmic history, collections of atoms have arranged themselves into structures capable of understanding the cosmos and contemplating its end. As we continue exploring the mysteries of the universe, we might find evidence that strengthens or weakens the probability of these doomsday scenarios. The resolution of the measurement problem in quantum mechanics, the development of a consistent theory of quantum gravity, or the detection of primordial gravitational waves could dramatically reshape our understanding of cosmic stability. Until then, we exist in a state of profound cosmic uncertainty, aware of potential apocalyptic scenarios but unable to assess their likelihood with precision. Rather than inducing paralysis, this uncertainty might inspire us to appreciate the remarkable improbability of our existence and to pursue knowledge with greater urgency. In a universe that could end without warning, the pursuit of understanding becomes not just intellectually satisfying, but existentially meaningful, a defiant assertion of consciousness against cosmic indifference.